We address the problem of embedding structure onto complete and partial shapes. Using structure, we can annotate shapes with their semantic parts. We also recover and fit similar objects from a shape collection to match a partial scan. At the core of our method is a set of simple structure-aware templates. We can fit these templates to individual shapes through optimization. Real-world objects often follow visible structural patterns. These patterns provide higher-level abstractions beyond detailed geometry. They can tell us more about an object than finer details like dimensions, style, and fine-grained appearance. The structural parts of many real shapes can often be approximated by simple geometric primitives, like 3D boxes. We design simple shape templates to model different structural patterns of shapes. The templates are made out of box primitives and encode spatial relationships between shape parts. The dimensions and locations of the boxes can be adapted to fit a shape. Fitting the template to a shape projects a sense of structure on it. Template fitting is done by solving a non-convex optimization problem. We use an evolutionary strategy algorithm to avoid local minima and run with multiple generations to obtain an optimal fit. We assign structure templates to all shapes in the ShapeNet repository. We fit all possible templates to all shapes of a given category. For each shape, we select the best fitting template. Using the templates, we can transfer structure onto partial scans of shapes. We employ a declassification network to select the template for the partial scan. The same network assigns a cluster in the shape space. The network is trained on simulated partial views of shapes in the repository. The network predicts not only the right template, but also good initialization for template fitting. The optimization then fits complete templates to the partial scan. The constraints encoded in the template hallucinate the missing structure. The template fitting helps select the closest shape from the repository. We can manipulate and deform this shape to match the template of the partial scan. This recovers a fully meshed shape that accounts for the partial point cloud. The deformation is structure-aware and linearly combines the transformations of individual template boxes. As a result, it preserves the shape's local properties. The heat map indicates how much different parts of shapes deform. Red and blue highlight the areas of maximum and minimum deformation, respectively. Using our pipeline, we can recover a full CAD mesh that matches the partial point scan. This can be used to replace part of a scan 3D scene with a mesh. Applications include scene modeling and editing for AR or visual effects scenarios. The optimized templates allow for part annotation, which effectively transfers structural information onto the shape. This can be done for all shapes in the database. And for partial scans as well. To recap, our pipeline can infer shape structure. By embedding structure onto partial point scans, we can complete, label, and recover their shape. We demonstrate these tasks as applications.